CERN and from here. And she will talk about asymptotic puzzles and accelerated expansion.
Okay, does it work? Yeah. Okay, so thank you very much. Thank you to Luis, Fernando, and Angel for putting this wonderful workshop together again. We are back to the swamp, and I'm very happy to see how many people. I'm actually surprised how many people are. So my plan today is to talk about, well, this paper about whether we can have asymptotic accelerated expansion, which will actually appear tomorrow in arXiv. So this is going to be like the trailer, and then you can check the paper for all the details. If you like the trailer, you can see the whole movie. And also at the end of the talk, I will tell you a bit about some asymptotic puzzle. There are a few things sometimes when you study all these factors and the distance conjecture that you find numerical coincidence and puzzles that you don't know how to explain very well. And I thought it might be nice with this familiar audience to share it and see if we can have some discussion during the week. Okay, so let me start with my favorite asymptotic limit. So studying the physics as the infinite distance limits is one of the central ideas of the swampland. We have progressed a lot since a few years ago, understanding better both the distance conjectures of how the towers appear at infinite distance, and also regarding the asymptotic behavior of the potential. So what happens asymptotically, like very far away in the modular space? And this is, sorry. Okay, just like not full screen completely, but okay, fine. Like this. So I think we are in a moment in which it's clear that in string theory we had these behaviors, but the tricky part is to make this precise. And I think we are ready, and as we have seen in Tom's talk, we are at a moment now in the swampland program in which we can start really asking more refined questions and really sharpen all these ambiguities, all these order one factors, and so on. And this is good both for phenomenological implications, of course, for inflation, the existence of dark dimensions, like towers of states in our universe, and so on and so forth. And also for quantum gravity itself, like regardless of, like understanding what happens asymptotically is like understanding what are the possible quantum gravity resolutions that I can have. It's like classifying the possible quantum gravity theories. When we talk about the emergent string conjecture and we say everything is the compactification or string perturbative limit, that's actually very strong. We are saying that the resolution coming from quantum gravity is either involves extra dimensions or strings. Like, so it's really like understanding what are the possible quantum gravity theories. Now, in this talk, I'm gonna ask one of these refined questions, which is whether we can have asymptotic accelerated expansion in the universe, which is correlated, as Tom described before, with these exponential factors. Okay, so very quickly, we have this runaway behavior, very well known since many years, much before this plan, right? Like Dan Cyber and so on. It seems that this runaway behavior occurs at every infinite distance limit. There are works trying to show this and so on. And one question, of course, that's an old question, is whether this is useful for something. Whether one can, for instance, construct some quintessence model with this runaway, right? Describe some scalar rolling down the potential and describing the accelerated expansion of the universe. Now, of course, the runaway is not enough to have a quintessence model. One of the things you need to satisfy is that the exponential rate is not too large, okay? It cannot be too steep because otherwise it doesn't yield acceleration. Now, of course, to get quintessence, you need many more things. And like this is just like the first obvious thing. There are many more phenomenological issues that you need to satisfy, which I'm not going to consider here. What I'm interested, can we make this like full screen? Preview. Slideshow. Okay, better, right? Good. So what I'm interested is just whether string theory can describe accelerated expansion asymptotically or not. Okay, regardless of whether it's good for our universe. I mean, that would be a second question. Now, maybe before this, so let me remark that this is something that now it's an interesting question in the context of the swampland, because there are bounds about how exactly, what should be exactly the value of this exponential rate. Okay, so we had the TCC bound, we had this strong de Sitter bound that Tom proposed. Maybe I should also mention that already in the TCC paper, they also mentioned this bound for exponentially decreasing potential. So there are some proposals that would actually forbid accelerated expansion. Is there no way to take this out? Okay, anyway. Okay, so let's try to check this. Okay, now, if you have some scalar potential, which is a sum of different terms asymptotically, let me consider, because this is going to be the general case that we will study in my talk, when you have flux compactifications, asymptotically, this potential behaves like some monomials of the different sections, like the different scalars, the non-periodic scalars that you send to infinity. And you have the typical minus log behavior, okay? Next, I mean, we will justify this better coming from F theory and so on, but at the moment, let me just assume this structure. Now, once this is fixed, we study in the paper what are the possible asymptotic trajectories. And if you really want to go parametrically far away, what you have are these gradient flow trajectories, okay, that take this form. And what you need to do is to find what is the exponent, like this beta, what is the trajectory that would maximize this slope, okay, so that one finds the gradient flow trajectory, okay, that has the steepest descent. So it's a sort of optimization problem that is not, I mean, it's trivial if you just have one scalar, but it's not so trivial if you have many scalars. So the first thing I'm going to do is to reformulate this optimization problem in a more pictorial way that we love in the swampland program in terms of a convex Hall condition. Okay, so it happens that this optimization problem is equivalent to take all the terms of the potential. So each term, I'm going to compute what we call like this de Sitter ratio. So that's the ratio between the scalar, the derivative of the potential over the potential. Okay. So if you just have one term, this is going to be this de Sitter coefficient, the exponential rate. But if you have many, you have to define it for each of them. And then the gradient, like the full de Sitter coefficient, is going to be the distance to the convex Hall of all these de Sitter ratios. Okay, so you can see that if you want to satisfy these de Sitter bounds, like for instance, avoid, like forbid asymptotic accelerated expansion, what you need to satisfy is that this convex Hall of all the terms in your potential lie outside this ball. Okay, now this is, as I said, this de Sitter coefficient just becomes the distance, so that's why you need to be outside of the ball. Okay, so that is bigger than your given bound. And these de Sitter ratios, let me mention, they look quite similar. Like if I have a flux potential, you can have a dual description in terms of the membranes that are charged under the dual free-form gauge fields. And these are like the scalar charge to mass ratio of these membranes. Okay, so this de Sitter conjecture actually is like a scalar with gravity conjecture for the membranes, with the difference that we need that all the membranes satisfy the bound, in the sense that you need the convex Hall to be outside, not to contain the ball, which means that it's not enough that you have some subleading terms that satisfy the bound. You need that the leading terms of the potential satisfy the bound to avoid accelerated expansion. So it's something, I mean, to require the absence of accelerated expansion, for instance, like to satisfy these de Sitter conjectures, is something stronger than the usual with gravity conditions that we are used to, in which only some states need to satisfy it. Okay, good. Now, once we have this, it's quite easy actually to try, given a potential, check if it satisfies the conjecture or not, and what is the de Sitter coefficient. And there are mainly two scenarios, which I want to remark, because they are, well, you will see why they are important. The first case is when you have a single dominant term, okay? So the potential in the end, I mean, asymptotically, when you take some limit, some scalar going to infinity, there is one term of the potential that dominates, and pictorially, like the distance, the shortest distance goes to one of these points, and that's it. Or whether there are several terms that compete asymptotically, which can occur when you have more than one modulus and they grow at different rates. So it could be that then several terms of the potential compete, and then the shortest distance is not like it's in the convex hole, it's in the middle. Okay, so I put here some examples. The difference is that when you have a single term that dominates, when you compute the gradient flow solution, you have a full family of solutions, okay, that satisfies this. Just the exponent is fixed, but you have a different family with different factors. And when there are several terms that compete asymptotically, what you generate is a sort of valley towards the infinite distance. In such a way, there is a unique gradient flow solution. Okay. Okay. So why I'm telling you this is because precisely this second scenario is the one that can violate the bounds. Okay. Because in these cases, as you can see, well, it's gonna be much easier to cut this ball, even if the individual terms are bounded. Okay, so this is the like bottom up. So let's try to check now. I mean, it's just a matter of what are the value of these points, okay, whether we have accelerated expansion or not. So let's try to see whether we can realize it. So first of all, we're going to focus on 4D equals 1 EFTs coming from string theory. And then the question is if there is any restriction on where these points are, okay? Like what is the minimum value that they could take? Okay, so first of all, even before going to string theory, we can ask the same question in supergravity, okay? And I want to do this because actually it was proposed, well, there's this argument in this paper that Tom elaborated recently, which seemed to forbid asymptotic accelerated expansion, not just in string theory, but even in supergravity, which is very strong. And I want to review the argument to see what is the loophole that one can have and how it matches with the two scenarios that I described before. Okay, so the point is that if you have 4D equals 1, let me just define this like using the superpotential and the Keller potential, this quantity, I call it the tension because it's like what corresponds to the tension of the membrane. So you just have the Kremmer-Tal formula of the scalar potential. And the point is that if this quantity, right, the derivative is proportional to the same quantity, then you can just plug this back. And you see that the zeta, no, the exponential rate of the potential is correlated to the exponential rate of the superpotential, no? In such a way that this de Sitter coefficient already appears here. So if you want a positive potential, you get a lower bound, no, for this exponential rate, which is actually square root of 6, which means that it's even bigger than the square root of 2 that you need for accelerated expansion. So there is no way to get accelerated expansion. Now, the point is that this is not always true that you have to satisfy this, especially it's not true in a scenario 2, when there are several terms that compete, because when you take the derivative, you just don't get the same function. You could say, but if I'm going very far away asymptotically, in the end, I have one-dimensional trajectory. Why I cannot forget about the higher modular space, just consider this trajectory and apply the argument, like what's going on. No, and the point is that it's not true in general that the gradient flow associated to the superpotential or to this tension is the same as the gradient flow associated to the scalar potential. So when you compute the derivative, there are more terms appearing here, and this does not hold. Okay, so this is a bound which actually works very nice in a scenario 1, but doesn't work in a scenario 2. Okay, so this fine, like a scenario 2 is a way to prevent this in supergravity. And from the convex Hall condition, you can imagine that this is precisely what is happening, that even if the individual terms are bounded because they are positive and they have a minimum distance, the convex Hall can still cut the ball. And it's not only a ways of thinking, like we check there are concrete examples in type 2A with all the model stabilized, that you get these type of situations and you get some de Sitter coefficient, which is smaller than this square root of 6. You could say, okay, how small can it get? Okay, how much can I push it? Well, if I have several terms and I have several moduli, I don't need all the moduli to be in the denominator. Like I can have some numerator, denominator, so that in the end, the potential goes to 0, but take into account that the moduli goes to different rates. So these points, they don't need to be in this first quadrant. They can be whatever. And if I want it to be positive, they just need to be very far away. But still, this can cut the ball at a very short distance. So from this supergravity perspective, there seems to be no bound at all for the de Sitter coefficient, which is good because it means that if there is any obstruction, it's not something of supergravity, it's something of quantum gravity. Okay, so it's really some Planck constraint, which what we like to study in this workshop. Okay, so let's see now in quantum gravity. Let's see if there are additional constraints that we have to impose. Okay, so let's go to string theory. Now, of course, there have been works studying the behavior of the potential asymptotically, trying to engineer quintessence and so on. I have here just some recent references. The point is that so far, all these works were always focused on the weak coupling and the large volume point. And what I want to say is that this is just one of the possible points. And still, I was surprised that only by studying this asymptotic limit, like some papers even concluded that it was not possible to have asymptotic acceleration at parametric control at any asymptotic limit string theory, which might be true in the end. Maybe that's what happens, but I think we should give it the same credit that we give to the distance conjecture, right? In the distance conjecture, it's not enough to say, okay, when we decompactify, we get the Kaluza-Klein tower, that's it. The distance conjecture is satisfied everywhere, right? In quantum gravity. Like, really, it's really hard to prove that all asymptotic limits satisfy it, and that's what we've been doing the past few years. So all I wanted to do here is try to do the same for the potential. Like, let's try to check other asymptotic limits. Let's see if it still works, whether these numbers, because we are really asking about what is the specific number, okay? And the specific number is going to depend on the type of limit. So let's try to get more data about what these numbers are. Okay, so this is, of course, not even here, like we can prove general limits. We're going to take some setup. And in order to go to different limits, we are going to go to different limits in the complex structure moduli space, because then we have all this machinery of a structure that allow us to determine the asymptotic form of the scalar potential at different points. Okay, and we can compute the value of the de Sitter coefficient in each of these points. Okay, so we do this, and the de Sitter coefficient, I'm not gonna, this is where you should check the paper and all the pages of work, but the point is that just once you pick the asymptotic limit, this is going to determine what is the gradient of the potential, okay? Just determine in terms of some discrete data that characterizes the limit and that you can compute. And the result, we have different tables, different examples, but in practice, I guess what you care about is whether we find any example that has a value which is smaller than the square root of 2. The answer is that we get only 2. They are from several. Let me tell you what these examples are. So, to our surprise, there is already one example in type 2B at weak coupling and large complex structure, which has some value of gamma, which is even smaller than what is the TCC bound. This is, I should have put it here, this is like the Ramon F2, 2-form flux, and then the reverse flux. That's it. That's all you need. And then there is another example in a different asymptotic limit, which is not weak coupling at all, like some other limit of F theory, in which you also get some value, which this time is just smaller than the strong bound, but bigger than the TCC. Okay, so these are examples that show that at least at the level of the flux potential, there is no like the bound is not satisfied. Okay, you can get smaller values. And all these examples is very important that they realize this scenario too. There are several terms that compete asymptotically. Okay, as you can see here, these are the two terms that compete, and here these are the two terms that compete. Okay, okay, good. And also let me remark that even if this is just at the level of the flux potential, it's the first time that, like in these Calayo compactifications, we get such small numbers, and they are smaller than what was found in previous bounds, because so far all the previous works were always considering the scenario one, which you have just one term. Okay? So that's the reason. Okay, good. Now, caveat, of course, this is not a model of accelerated expansion. Okay, just a model in which this gradient is smaller, smaller. But right now, what I'm showing you is just the complex structure modular space. So of course, to have a full model, you also need to consider Kähler modular stabilization and so on. And could be that once you study Kähler modular stabilization, maybe this is not possible anymore. Now, of course, the overall volume, we need to stabilize it anyway if we want to have a quintessence model, because it wouldn't be consistent with the experimental bound. So it's something that one has to address at some point. So this is not a full model, but just wanted to see if at least at the level of the flux potential, we can reduce the number from what we have found before, okay, like the first step. Okay, good. So let me make, good. So let me make a few comments, then the relation to the distance conjecture, and then I will finish with the puzzle. Okay, first, we are checking what is the exponential rate of the potential. How does it compare with the exponential rate of the tower? Is it compatible? What is larger? What is smaller? Well, it's very hard to, it's what I was saying before, it's very hard to find this tower of states in the complex structure modular space and to identify which one is the leading one and so on. So at least, but at least what we can do is to check what is the exponential rate for the tensionless strings that we get in this limit. Okay, so in this 14 equals 1, she studied with Luca, Fernando, and Stefano. There seems to be always a BPS string that becomes tensionless asymptotically, and this at least will give us a tower. There could be other ones that are lighter, but at least this is one. And the exponential rate is completely fixed by the geometry, so we can just compute it and check. And indeed, one always gets that the potential scales with the mass of the tower to some power. And funny though, in the example which was violating the TCC, it seems weird because this power is 1 while the other one is 2. So this can be problematic, right? Because it seems that you get a tower which is below the Hubble scale. So maybe you can, I mean, probably you cannot trust this example, or once you take it into account, there is no accelerated expansion anymore. It's funny because actually this is a very normal limit, like that to be just with F2 and H0 flux. So, I mean, I was a bit surprised. So maybe something to understand better in the future. But the other one seems okay. Like you just have a tower saturating the Higuchi bound. Now, let me comment also to refer to the nice talk by Tom before, that if one assumes the lower bound for distance conjecture that he was describing, indeed, as he discussed, and well, if one assumes this bound and also this relation between the potential and the mass with this factor bigger than 2, then it's true that you cannot get the accelerated expansion. So you could say, okay, what is going on? Like now there is a beautiful story, what could fail? Well, I see 3 options, like to be completely open. One is that indeed this is preserved. So these examples, once you study Kähler modular stabilization, they don't work. Maybe you cannot stabilize Kähler moduli, I don't know. You cannot generate hierarchies or whatever. So that's a perfectly well solution. Another solution is that then this doesn't work. Maybe the complex structure modular space is special, like before I was saying, like I don't know how to identify the towers and so on. It's the second option. And the third option is that maybe what doesn't work is this. Let's have the 3 options. And you could say, okay, could they happen? So what is the argument behind this? Okay. Now, one of the arguments is the Higuchi bound, right? Like if the tower has higher spin fields, you would expect that the mass has to be above the Hubble scale. Still, I think one should revisit all these things with quasi de Sitter scenarios and so on. Like it's not exactly de Sitter, but okay, I think it makes sense that they still apply. But this is very clear if the tower is three modes. If they are Kaluza-Klein modes, then you could say, okay, maybe I don't have only Kaluza-Klein modes of the scalars, but I will have also Kaluza-Klein modes of the gravitons. But here I'm kind of assuming the same scale for everything. I don't know, maybe there is a way when you study Scala-Villot compactifications that you get still a bit of a gap between the scalar and the higher spin modes, such that you don't have to satisfy this for the scalar ones. Like here, we are really imposing that the mass of the lightest one is smaller than Hubble. It's one option. This could be consistent with the fact that even if you don't satisfy this, I mean, all these examples and these statements, like these two bounds with, I mean, this bound is still consistent with accelerated expansion if one just imposes the weaker condition that the potential is below the species scale, okay? So this is still fine. Like if you just want that the potential is below the quantum gravity scale, you can still have accelerated expansion. What forbids the accelerated expansion is the relation with the mass of the tower, not the quantum gravity scale. So there are the three options and things to study in the future. And then I will finish. So what I'm going to do, let me summarize what I just said, and then I finish with the puzzle, okay, and we finish the talk. Okay, so we have studied whether string theory allow for asymptotic accelerated expansion using the runaways, the very well-known runaway behavior. We have reformulated this as a convex Hall condition to make more clear what are the features that the potential need to satisfy to have accelerated expansion, and what are the possible scenarios that are more realistic to realize it. We saw that it's something stronger than the usual convex Hall with gravity bounds, okay, because everything has to satisfy the bound. Something to think whether maybe for membranes the with gravity is stronger and everything has to satisfy the scalar gravity, I don't know. And then by checking concrete examples in string theory, we have found that this bound can be violated at the level of the flux potential. It was very important to achieve this, to consider examples with several terms competing and going to different limits in the modular space. And of course, the caveat is that it's not the end of the story. One has to stabilize the moduli and see if it survives or not. And now let me finish with the puzzle. Okay, so I think, as I said before, I think we are in a moment in which it's beautiful how everything is coming into place, coming together, all the factors. Like, I think we understand much better what are the possible quantum gravity resolutions, like they classify the different limits. And I really believe that in the very short term, I mean, we are gonna get rid of all these order one factors. Very optimistic. And everything is working very well in flat space compactifications, okay? So, and this emergent string conjecture, which I then should have put the reference, but Timo, Wolfgang, and Assyrian, it's very useful as an organizing principle, right? Because it tells you, okay, everything is string perturbative limit or the compactification, and it's beautiful to see how even the exponential rate that you get match with the microscopic quantum gravity resolution in string theory. Beautiful. Okay, so the puzzle is, what about in ADS? Okay. Now, in ADS, we also can classify these towers. Let me just go very quickly. It's just going to be one slide. But in ADS, the bulk modular space maps to the conformal manifold. This exactly marginal operators. Field metric is the Samorfikov metric. And instead of tower of light phase, what we get are tower of operators at in the unitarity bound. Okay. So by studying this in the conformal manifold of the CFTs, what we seem to find is that there is always some infinite tower of higher spin operators, okay, that's saturated unitarity bound at infinite distance measured by the Samorfikov metric. Okay, so this means that there's always a free point, and this is beautiful because it allows you to compute exactly what is the exponential rate in a very general way. Okay, so this is going to be just the last. So this is the exponential rate that we got. Okay, this is the central chart, the dimension of the gauge group. Okay, and the point is that, okay, now we can check what are the possible values that we get. So we compute the exponential rate for, in the paper with Leonardo, Eric, and Kumru, we computed the exponential rate for all possible 4D superconformal field theories with simple gauge groups. And the result was there were only 3 possible numbers. Okay. Now, these 3 numbers happen to match with what you would get, not with a string perturbative limit, which you would expect because this is a tensionless string. This is a tensionless limit, it's a higher spin tower, but it matches with what you would get from the compactifying to 8, 9, and 11 dimensions, just because. So just wanted to share this because maybe it's just a numerical coincidence, or maybe it's hinting, I mean, if we really trust all this story, that somehow this tension is the sigma model of this tension limit, somehow has some dual description to the compactifying to other dimensions, something like that could be something deeper in quantum gravity. And I'm telling you this not just because this way you can just start a project and not tell me anything about it. I just want to share it with you because I find it very exciting. And I'm happy if you come to me if you're interested and we can talk and discuss and I can give you my thoughts. Maybe we can make any sense of it. So thank you very much.
Well, we're now running out of time a little bit, so I'm going to allow 1 question. And maybe 2, but that's the maximum.
Thanks, Irene. It's more a remark, I'm afraid, but it's a positive remark. So in the cosmology literature, there's something called generalized assisted inflation. Maybe you know this. And there people have looked at exponential potentials, which are a sum of various exponentials. And in all those exponentials, you have many scalar fields. So they're all coupled. And then they have a general formula for what is actually the dominating gradient descent flow. But then there's one worry. So in that literature, they've shown that whenever one of the exponentials is negative, these trajectories will always be unstable in the sense that they're sort of top of the hill. And that is very similar to these classical de Sitter solutions, where imagine one day you can get it at small coupling, large volume. They've always been tachyons. So I'm saying I'm expecting that there's existing literature which might show that, because you always have a negative term.
Yeah, so the thing is that in these potentials coming from F theory, like the complex structure moduli space of F theory, because of the theorems of hot structure, you can show that at leading order, all these terms are positive. So actually, we have an appendix in the paper to show that there are no tachyons.
But if you stabilize all moduli, you always need orientifold. There will be always one term which is negative.
No, that depends. So we are in the complex structure moduli space.
Yeah.
Right. So before you just think of the complex structure, like the potential is positive definite, right? Because you have the noise scale. When you go to T2A, then you can have some terms that are negative.
Well, the potential is
which one dominates.
I agree. The potential is positive, but there's at least one negative term inside.
The ones we consider are positive by Hodge theory.
Okay, and then if time for just a very quick remark. Okay, yeah, then I'll.
I think